Okay, in this short lecture we're going to return to our RC circuit, and we're going to use impedance to find the complete solution, in this case for the current flowing in here. We found that R1 was 2, we were given R1 was 2, R is 4, C is 1/4 of a farad. And we had already found that the impedance function, looking into this terminal, was 2 times S plus 3 over S plus 1. We also noted that when you turn, let's find the homogeneous or natural response, which we've already done. Let me just recap. Natural response found by turning Vs off. Okay, we found that let's see, Vs is equal to Z times I. This will be our homogeneous solution here. Therefore, if Vs is equal to 0, then we need to find the zeros of Z of S. Alright, zeros of Z of S give us, we're looking for the pole. In this case it's going to be S equal to -1. Alright, that's our pole. And therefore the natural response for the current is going to be of the form A e to the -1t. Okay, so that's our homogeneous response. Now we want to find the forced response. Let's suppose that Vs is equal to just some constant Vs. Right? In other words, it's equal to a constant times e to the 0t. In other words, S is equal to 0. Now we're going to have different S's that we'll find for that correspond to the homogeneous response and that correspond to the particular response. Right? The homogeneous response will have S's that are that result from the internal characteristics of this network. In other words, the resistances and the capacitance, essentially the time constances that are involved here. The forced response will have an S that is determined exclusively from the forcing. So in this case we're forcing it with an e to the 0t, so let's find the response that will occur when we have an e to the 0t excitation. So we look at I, and I'll say particular now. I is equal to Vs over Z. Alright? And we'll have, since Vs, and I'll say, let's write it this way, where S is equal to 0, therefore Z of S, where S is equal to 0. Okay, so let's plug that in. We'll have Vs divided by, alright, and if we plug in 0 for the impedance, we'll have 2 times 0 plus 3 over 0 plus 1, which will give us 1/6 Vs. Now if we go back and look at the circuit, it's clear that that's what we'd have for the particular solution. You could have told me that without knowing anything about impedance. When we were initially approaching the problem of a particular solution to an RC circuit and we applied a constant voltage, we said, okay, with the constant voltage the capacitance is going to open up, so there's no capacitor. What does the voltage source see? It simply sees, in this case, 2 resistors in series. So we have Vs and we have some current. That's exactly what this is giving us, because it's 2 ohms and 4 ohms, so 2 plus 4 is 6. Now we can write the complete solution. So we have I is equal to I homogeneous plus I particular, which will be A e to the -1t plus 1/6 Vs. Now we need to satisfy initial conditions. Satisfy initial conditions. Suppose that I, well, let's see, what do we have? We have V. The initial condition would be a capacitor voltage is equal to V naught, some initial voltage. So if that's the initial voltage, what will be the initial current flowing? Well, we have this resistor R1, and we have at this end, we have Vs, and at this end, we are told that Vc is equal to Vo. So the current flowing here is simply going to be Vs minus Vo over R1, which is equal to 1/2 there. R1 is 2. So therefore, we can write the complete solution IT is equal to, well, no, I guess we're not quite there yet. We still have to find A. I apologize here. Okay, plus 1/6 Vs. And when we evaluate this at time equals 0, we're going to find that we have A e to the 0 plus 1/6 Vs, right? Now it's this current that has to be equal to our initial current. Call this I naught, right? Which that initial current comes from the initial voltage across the capacitor. So we have I naught, and that is equal to 1/2 Vs minus V naught. So therefore, therefores, A is going to be equal to 1/2 Vs minus 1/2 V naught minus 1/6 Vs, or in other words, 1/2 V naught plus 2/6. Is that right? Yeah, 2/6 or 1/3 Vs. And now we can write the final solution. I is equal to 1/2 V naught plus 1/3 Vs, okay, e to the minus t plus 1/6 Vs. That is our complete solution. And what does it look like? Well, in the end, after all the exponential term dies away, we'll end up with 1/6 Vs. And that makes good sense, right? If you think of what we have, now go back to this, go back to here. The voltage here is at not Vs times 4 over 2 plus 4. Right? In other words, 4/6 or 2/3. Why don't I have 2/3 here? I got mixed up. I'm solving, my solution is for current, and here I just wrote an expression for voltage across this resistor. So these are consistent with each other. I'm just looking at two different things. So forget that. Okay, and then we have this exponential term, 1/2 Vo plus 1/3 Vs, which could be positive or negative. We don't know until we choose Vo and Vs. But it would look like this, or it could look like this, right? But in the end, it's just a common decaying exponential that settles out at a DC value. And so there's a complete solution using impedance. Okay, we're going to look at another example that will expand the use of impedance beyond what we have looked at so far. So far, I've drawn everything as a one-port network, right? This Z sub S, and then you either have a voltage source across here or a current source, and we're either looking for the voltage or the current or the voltage. But what about the following circuit? Let's say that we have Vs here. You have a resistor, and let's say that I have an inductor and another resistor. Let's keep this simple here. Okay, R1, R2, and L. And what if I'm asking for the current IL? I want to know what is the current IL. And specifically, we're going to say IL, of course, is an I homogeneous plus an I particular. But let's focus on the homogeneous. How do I find that? The only thing we know so far is we draw a box around here, and we could talk about this current. But now I'm asking for that current. Okay, so it just takes a little trickery. All right, so let's first, because it's homogeneous, turn off VS. Right, so I'm going to have this network here. All right, I'm looking for the homogeneous solution, IH here. All right, so that's the first step. Then let's just redraw this. So this is R1, R2. Let's put R1 over here. We're still at the same place. I'm going to move R2 over here. I'm not rewiring anything, just moving how I've laid it out. And then I'm going to put inductor L like this, and I'm going to draw this to ground. Okay? Same circuit, same topology. I've not changed anything. But now you see I can actually draw a box around here, right? And I can say, what is the impedance looking into here? And because I have a short, right, this is a short, I'm looking for the natural current response. It's as though I had a voltage source, here, and then I've turned it off. So the impedance in this case, looking in, is going to be SL plus R, I'll call it RP, where RP is parallel of R1 and R2. Okay? And so in this case we've got this voltage, V, we'll call it V is equal to Z times, I guess it'd be times minus I, okay? But V is 0, right? So it's, never mind the minus I, that doesn't factor in. I just have I, Z times I. Therefore, we're looking for the zeros of Z sub S. What are the zeros of Z sub S? Well, we have S plus RP, well, we have SL plus RP is equal to 0, or S is equal to RP, S plus RP over L is equal to 0. Therefore, S is equal to minus RP over L, or we'd say that's our 0. And now we can write the homogeneous solution form. It's going to be some constant A e to the minus RP over L t, or we could write it as A e to the minus t over tau, where tau is equal to L over RP. And we can do the same thing if I were, let's say that we had a circuit like this, okay, and it wouldn't matter what the source was over here, whether it was voltage or current. Let's go ahead and do current here. Right? Now I say find the voltage here, find the homogeneous response. Well, all I would do is I would turn off this current source, if that's indeed a current source. I would go ahead and, let me just wire this up, redraw this. Okay. And now I'm looking into this port here. Right? It's kind of like I was driving it with the current source, and I'm turning it off. This is the voltage that I'm looking for. So we'd simply have Z of S is equal to 1, well, it'd be Z of C in parallel with, in this case, R2 plus R3, and then we'd proceed from there. Let's work another example using the same RRC network as we had before. The difference this time is that we're going to define V of S as not a constant, but as an exponential decay, minus 2t. Alright, and what this is this exponential decay that at time 0 is equal to 6. Alright, note this is not 6e to the minus 2t u of t, right, which would look like this. It would be 0, then it would pop up to 6 and come down. That's kind of like the difference between saying V of S is equal to 6 and V of S is equal to 6 times u of t, right? In this case, it's been 6 for all time, and in this case, it steps up to 6 from 0 at time 0. So we're looking at this case here. And what we're after is we're looking for what is the complete solution I of t, okay, for t greater than 0, greater than or equal to 0. So one, we have I, well, we know that I of t is equal to the homogeneous plus the particular solution, right? Homogeneous we have already found before. We can write that as when we're looking for I, it's equal to V divided by Z of S, and so we're looking for the zeros, okay, zeros of Z of S. The 0 of Z of S in this case is, looking over here, is when S is equal to minus 3. So we have IH is equal to A times e to the minus 3t. We found this in the previous example. So this is just repeating that. If you need clarity, go back to the previous example. Now the particular solution, how do we find that? The particular solution IP, call it, is equal to Vs, I'll say Vs of t comma s, right, divided by Zs. And I guess I should put s over here as well. This is 6 e to the minus 2t, right, divided by z of minus 2. Right? We need to use the impedance that corresponds to the frequency, if you will, the value of s at which we're exciting this. So z of minus 2 is equal to 2 minus 2 plus 3 over minus 2 plus 1. So that's 2 times 1 over minus 1, or minus 2 ohms. Therefore, the particular response is equal to, I'll take the s out now that we've plugged a number in for it, is equal to 6 e to the minus 2t divided by minus 2 ohms. This gives us minus 3 amps times e to the minus 2. Finally, the complete solution is therefore I of t is equal to the homogeneous, which is a e to the minus 3t, plus, I'll say minus, 3 e to the minus 2t. Now satisfy initial conditions. I at time 0, let's see, I at time 0 is going to be equal to Vs at time 0 minus Vc at time 0 divided by R1. That's equal to 6, right? 6e to the 0, minus, and we are given the initial capacitor voltage, it's 0, right? Did we specify that? No, I did not. Let's say this is the voltage here, Vc, and we'll say Vc at time 0 is equal to V0 is equal to 0. Alright, that's our initial condition. So V0, and we'll say this is 0, divided by R1, which is 2 ohms. So we have 6 volts divided by 2 ohms, or 3 amps. So therefore I0 is equal to 3 amps. Now we can write I of 0, let me just go up here, equal to 3 amps, which is equal to A times e to the minus 3, 0, minus 3 e to the minus 2, 0. So we have 3 is equal to A minus 3. This gives us A is equal to 6. So finally, we can write the current as 6 times e to the minus 3t minus 3 e to the minus 2t for time greater than or equal to 0. Let's look at each of these. We have, it starts at 6 and decays pretty quickly. And this one starts at minus 3 and decays more slowly. So you put these two together and we end up with something that looks like this. At time 0 it will be 6 minus 3. Alright, so I'll put 3 up here. Be 3. And then it'll come down negative a little bit and then do this. Didn't draw that too well. It'll go to 0. Okay. The reason that it goes negative is that this is a tau of 1/3. This is a tau of 1/2. Okay, so the positive signal here decays quicker than the negative signal, and so there comes a point when there's a residue of the negative signal that is greater than the positive one, and so this dips below. So it would do something like this. All right, and this is significant. What have we just solved? We solved for the complete response of a linear circuit that had an initial condition and that was forced by a signal that was not constant but was an exponentially decaying signal.